So I chose to talk about this subject. Now this subject is big, and several people will be talking about this. So I won't be talking about all emerging directions, which will be nearly impossible. It's coming. Yeah. Okay. You're okay? Good. Fine, all fine. Thank you. So if you look at the world, the periodic table with which the world is made of, which is right here, this periodic table, world is made of this. Right? But world is made of macroscopic materials. World is in those macroscopic materials, like this in concrete and buildings and all that. The constituent materials are also large micron size objects or millimeter size objects. We call them bulk. But a big renaissance is happening in the materials world. Can matter, as we see, can be made of nanoscale objects. So this quest of creating the world with nanoscale objects is expanding, and without that thought, sustainability is impossible. For example, we are looking at a world in which carbon dioxide can become methanol, for example. Without nanoscale materials, this is impossible, as we know catalysis today. But we are already using them. For example, carbon monoxide is converted to carbon dioxide in your petrol engines or diesel engines using nanoscale objects. But petroleum refining is happening with nanoscale objects. You are removing sulfur from petroleum by nanoscale molybdenum sulfide. So likewise, there are hundreds of examples, whether it is hydrogen, whether it is photovoltaics, whether it is sensing or communication or radars or what have you, or diagnostics, biology, delivery, nanoscale objects are central. So the world is becoming nano using materials derived from these periodic tables. Now in that area, a lot of excitements have happened, and this area won a Nobel Prize. Another set of people who are also working on nanoscale objects won Nobel Prize this year. So in that broad subject of materials becoming nano, something new that has happened in the very recent past, about 10, 15 years, is that matter has also become atomically precise. So if you take gold, you can have today a particle having just 25 atoms. And it's not just that you have 25 atom gold as an unstable, reactive object. You can today buy a gram of that or make a gram of it. And that is protected with some ligand, 18 of them. It has inherently 1- charge, just like chloride ion having a charge. Similarly, it has some charge. Correspondingly, it has a cation. Most commonly, there can be some sodium ion present there. So this object is now a crystal, can be crystallized if this is there. And crystals look like these. This is exactly not that material, but crystals look like this. And if you have well high quality crystals, just single crystals, you can do diffraction. So we can get crystal structures. So this is structure derived from that crystal. And if this is so uniform, why not you put it in solution and measure a mass spectrum? Yes, we have a mass spectrum of that. So which means you can have NMR of it. You can have IR of it. We can have almost anything. That means once you have a structure, you have all these properties. I'm just going to quit this. You can have put this into computers like our dear friend Chaitanya does, and then understand the orbitals, understand transitions, predict properties, predict reactivity. So all of this is happening. Now this is about one molecule, but there can be many, many molecules. So today we have over 500 molecules of this kind. I carefully use this word molecule. This subject area for a long time, we never used this word molecule. We call them particles, clusters, but today we know that they are molecules. So today we call them as molecules, atomically precise metal molecules today. And so if I go back a little bit in time, no subject is that new, right? So if you go back in time, these are nanoparticles made by Faraday, 1857. And I do have some samples of gold particles that I made here for the very first time. Say, this is now, I would say, 28 years ago. Those particles are sitting there in the refrigerator. But something very new has happened from this time. These are something like particles containing 200,000 atoms of gold. But later on, people ask this question, is it possible, really, to create these clusters in the gas phase or particles in the gas phase? So this happened around the late 1960s. It was a struggle to get them. 1970s. Around the 80s, people started doing this well, and a great celebrated examples of creating particles or assemblies of atoms in the gas phase is the discovery of C60, 1985. So around then, lots of clusters were made. Then it was called clusters made in the gas phase. And this is one of those celebrated papers. So here you have sodium cluster. So evaporate sodium in a vacuum system and measure the mass spectrum of what comes out. Not really evaporate, but evaporation and something called cluster formation. There's a setup for that. And you see there is some cluster peak, a set of peaks here, a set of peaks here, something here, something here, some bunch here, some bunch here, some bunch here. Oh, what are these bunches? This is not sodium 1, sodium 2, 3, 4, etc. They realize that suddenly some magic peaks come up. Certain peaks have greater intensity than others. After this, no intensity, and something else comes up. After that, some intensity decrease. So all of these were understood as beginning of a new kind of matter. That is, something stable could be happening around certain kind of sizes, certain kinds of possibly shapes. Is it possible to make them? So this subject then expanded. Lots of people worked on this. Many, many people worked on it. And today, this is what it is. Lots of people. This is one such paper. Many papers. So this is now having over 2,000 citations. Lots of people worked on. Many are written here. Lots of people or lots of Indian fellows are here. And I'll show you some pictures of these. Now, if I go back, so what are they really? They are particles made of certain atoms. I said gold or copper or silver or platinum or palladium or all of those elements typically on the right side, all these elements. Now, they are now, if you start looking at it, they are starting from an atom at the center and some set of atoms outside forming an icosahedron. Around this, there are atoms, could be, or you could connect these atoms with something called staples. And these are sulfurs over which, on these sulfurs, there are alkyl groups or aryl groups. They look like these. So which means that there is a core, there is some staple entities, and there is some ligand. This is the general structure. So the quest for many years has been to create or know these structures, create more of these, know more of these structures, and understand their properties. And in that, today we are also getting into applications. So lots of things have happened. So look at this in some detail. Now I said 25 atoms. 25 atoms of gold. Gold's atomic number is 197. So if you measure a mass number or mass spectrum of this, you should get just one peak. But it has many peaks. Today's mass spectrometers, as you know, are quite advanced. So you have HRMS, high resolution mass spectrometry, and you can get mass peak 7390.5718. At 10,000 mass units, 0.0001 resolution is possible today. We have mass spectrometers with which we can measure not just 10,000, can measure a million in mass number. But not at this great resolution. There are friends of ours, we want to get one, a mass spectrometer with gigadalton mass, which means you can measure the mass of a virus. Now, this is all possible today, and somebody is waiting for a Nobel Prize. Gigadalton mass spectrometry. So if you take this 25 with ligand, 18 of them, there are many peaks. So I'll show you how this looks like. Now, it has 18, all these peaks because this ligand is typically sulfur containing. Sulfur has 4 isotopes, 32, 33, 34, and 36. It is typically having carbon, 12 and 13, hydrogen, 1 and 2. So all of these will give you a distribution, and that is the distribution that you're having. Now, when you have this distribution, what it means is that you can look at small changes in the distribution, which tells you what has happened to the material. So today in our laboratory, we look at this in great detail. Now you can also calculate what the spectrum looks like. So today we have molecules like these. Now in the lab, there's one student who makes molecules larger than these. So there are 300 atoms, 900 atoms of gold particles are made. So they look like these. Today we call them as new molecules. So the moment you say they are new molecules, you need techniques to see these. Look at this. This is unbelievable synthesis like organic chemists do. I am jealous of them because they make precise material, precise. So how about precision in nanoparticles? We say 10 nanometer plus minus something. No, precise. Tell me. So that is that precision today. This is 25 and this is 144. Precise. So today that is beautiful. And so this area is expanding. Lots of new things are happening. Now, world is not just ending here, right? A lot of people across the world, they are all clusters which have been made crystallized. And it is not ending there also. So this is expanding. Now, when you say this is expanding, there is space for you, right? There is space for you. Space for you, space everywhere. There is space for you. So for an organic chemist, it's great to see that this is actually some porous picture with lots of gaps. You can go and fill. Right? So you are actually seeing the old Mendeleev's dream with periodic table, lots of gaps, fill them. So we have written about it. We have written extensively about the world becoming nanoscale, with approaching materials with atomic precision. So when I say this in a winter school, it is also important to realize that we know very little. So this is water. You have lots of properties of water, precise properties of water. CRC handbook and measure this property. You ask what are the properties of water, you will see a lot of them. In fact, there are more than this, many, many more. You can write a book with water. But what do we know about gold 25? You have a molecular formula, we have a molecular weight, we have molecular structure, molecular absorption and emission, which I did not show you. I'm going to show you some molecular reactions just to enthuse you. Molecular assemblies, molecular co-crystals. But we know nothing about, is there a liquid phase for clusters? No, we don't know. We don't know. What are the electrical properties of this? What are the mechanical properties of this? What is the strength of this gold 25 crystal? Is it like gold 25? Gold? No. So lots of properties to be found. And that is where winter school becomes useful. You can go back and tell your advisor that, this professor said that this is a gap. So can I fill that gap? So we've written a book on this. Now, there are others who have written books. Lots of books. So lots of books have been written. There are lots of special issues have been there in this subject area. Accounts of chemical research, JAGs and others, physical chemistry. Lots of people have written. I'm going to show you some examples. So take a molecule like 25 or 38 or what have you, and that I said is soluble. You put it in an optical, in a spectrometer, you will get an absorption spectrum of this solution. And most interesting of this is that it gives you luminescence. And this is a man of luminescence. He studies all those great properties. So clusters give you lots of properties of this. Now one day I was asking, here is a cluster which is sitting like this, and there's another cluster which is sitting with another color. And you say that these are molecules? Can they react? So I asked this question some time ago, and the person who studied this is here sitting in this audience. His name is Krishnadas. So we studied this with mass spectrometry. So the paper came out like this, that we asked this question, between this cluster and this cluster, is there a reaction? This person is going to speak to you. He is sitting behind the last row. So asking the question, can you write a chemical reaction like this? When I say chemical reaction like this, what is implied is that there is thermodynamics in it. There is mechanism in it. There is dynamics in it. So there is a whole lot of details which would mean that these are molecules. So what Krishnadas did at that point in time was that you take this molecule gold 25, protect it with a ligand called fluorothiophene. It looks like this. S attaches to gold, H goes away. This is what happens. Now, if you take that molecule alone and measure what is called a matrix-assisted laser desorption ionization mass spectrum, you will get a peak like this and another peak like this. Those are the only two peaks that you will have in this if you have pure gold 25, FTP 18. You mix it with this. FTP is common here, that is deliberately chosen. Because in this area there is something called ligand exchange that happens. So it can complicate the mass spectrum. We wanted to avoid that complication. Ligand exchange of course happens, but it does not complicate the mass spectrum. Because mass is all that is measured and mass is common for both the ligands. So now you mix this, suddenly a peak comes. So you ask this question, what is this peak? This peak is the difference between the masses of gold and silver. So what has happened is, one gold has gone out and one silver has replaced here. So this is AU24 AG1 FTP18. Not that alone, one more gold has changed, 2, 3, 4, etc. And this so-called fragment also shows that. Now, while this is happening, there is another peak here. This also changes, which is happening at a higher mass and that is not shown here. You wait a little bit, this peak goes down, and after some time, this peak disappears completely. So you essentially did an atom exchange. So what you would call a substitution chemistry. You did substitution. But why should something substitute? Where exactly it substitutes? Remember that structure? You ask this question, where exactly does it substitute? You can ask this question computationally. So people like Chaitanya would do this computation. You take a 44 cluster and add one gold into it. Gold, as you know, is more noble than silver. So this substitution chemistry, your understanding of chemistry will tell you is computationally also it is possible. So energy is negative. This particular thing is not really enthalpy, it is delta E what has been computed, difference in energy. So you see all of these, whether you substitute at the icosahedral position, which I told you, or you substitute at, well, I did not tell you about this. 44 has a structure which has 4 different types of atoms. This is an icosahedral atom and a dodecahedral atom and some other position. Each one of these positions, it is possible to substitute. Not important right now to know all that. But gold 25, I told you there are 3 positions, which I showed you. There is a central atom, an icosahedral atom, and a staple atom. All these positions, it does not like silver to sit there because silver is less noble and all are positive. But if I do this reaction in such a way that this is happening, simultaneously this is happening, you do a computation, there is, in this molecule 25, the central position is replaced. Correspondingly, in 44, the icosahedral position is replaced, the energy is negative. But some things are all positive and negative and all that, but I for I substitution is negative. So one is icosahedral position, another is also icosahedral position, you have this. And you ask this question 2, what happens if 2 substitutions happen? There are more isomeric positions, you can compute all of these, but essentially thermodynamics drives this. You can have, I can ask this question, can this thermodynamics be universal? Well, is it universal? We did all those computations. Now you can ask this question, which chemical bond opens up and which closes first and all that. That gets you mechanism. So Krishnadas did many other experiments. So if you look at this chemistry, now 25 I told you, gold 25. There is also silver 25. You can have a reaction between these. Now when you do this reaction, something very interesting happens. So this you know is gold 25. 0 is to indicate that there is no silver in it. Now this is 25 0 to indicate that there is no gold in it. You mix these two, this is equimolar mixture, but they are molecules. So therefore, there is ionization cross-section. And this guy is weaker in ionization than this. So although it is equimolar, this is what happens. You have some peaks, and told you the reasons for this. Substitution chemistry, some reason substitution chemistry. In fact, if you expand it, there are many, many peaks, and all these are there. And these substitutions are more intense than other neighboring substitutions. Today we understand that this is because of entropic reasons. So there is greater free energy in these systems. If this is a 1- species and this is a 1- species, if they have to come together, then they should have a dimer. 1- and 1-. They come together and form a dimer. It is 2-. Do you see it? Yes, we can see it. And we ask this question, will this happen from this dimer? Other substitutions happen. We thought that this is what is happening. So something comes together and atoms go away, is what we thought, and we computationally modeled it. This is one cluster, is another cluster. They come together at very close distances because of supramolecular interaction to begin with. Atoms exchange. So Krishnadas did something even more exciting to say that you start with silver 25 and add a little bit of gold 25. So then you get a distribution. On this, you add a little bit more of 25, gold 25. You get another distribution, meaning more and more silver is substituted with gold. You keep on substituting, you can go all the way there. Lots of other peaks are there in the mass spectrum, should be there. This is not transmutation of silver becoming gold, but every atom can be substituted at nanoscale. Very interesting insight. So how do we understand all of these? Which atom changes? Why should it happen? And today to understand this, we have a scheme on nomenclature. I'm not getting into this detail right now, but to say that IUPAC has suggested that we should have a commission on nomenclature. So this is naming naked and monolayer protected clusters of IUPAC. Lots of people are there, and I'm there too. So this is what is happening today in this area. So just as organic molecules, we have a nomenclature. Can we have nanoparticle nomenclature? We call today these molecules as, let me just say what we mean by this. So if you look at a cluster in greater detail, every atom you can count, every ligand you can count, every chemical bond you can count, and you can ask this question, when this reacts with another cluster, which chemical bond is opened and which is closed, which can break, which cannot break. And if that is possible, well, if you wish to communicate that to someone, you need to have a nomenclature, a language. That language is not AU24AG1. So there, it does not say which is that AG. It does not say which is that ligand. So this is a language that is what is built today. And you might be wondering, how can this be reacting very fast? It's happening because there is a 12-atom core, as I said. There are 13-atom icosahedron. Around this, there are circles here. There is a red circle, blue circle, and green circle. They are all mutually perpendicular. And these mutually perpendicular something around a cluster is called aspicule. Or this is called a Borromean ring. This particular ring that you see is a Borromean ring. What is great about this Borromean ring is that if you cut this ring, which is a chemical bond, you can take this out. When you take this connection out, these two are also separated. This means that chemical bonds can be opened and closed just with one, or material can be opened and closed with one chemical bond. It's a beautiful thing. This is very much connected to Eastern philosophy as well. So we see many of these in our temples. So anyway, we call this as aspicules, nomenclature, leave all that. We can represent this on a board, and each one of these atoms can be counted on the structure, and which chemical bond can be opened, etc., can be done. Today, we also use these kinds of nomenclature to understand our clusters. Not just this kind of achiral clusters, we can also name chiral clusters. So interparticle reactions is a way to pursue this materials chemistry in greater detail. But what I just told you is only one tip of another iceberg. I told you that there is this cluster and coming together and forming a dimer. But this is not what is happening. You have a cluster, you have another cluster, they form a dimer. But this forms an atom exchange product. This is one atom exchange, and if you look at this in detail, this is 124 is this one atom exchange peak. So that is this peak. But this peak and this one, they can also form a dimer. And that dimer is this. And this invariably has one atom of one particular atom of silver and 49 atoms of gold. So because this is from 25 gold and Au 24 Ag peak. So this forms a dimer of that, and that is the dimer. In fact, this and this can also form a dimer. Many, many dimers. There are over 1700 dimers. And all of them converge to something unique. And what this means is a lot of very interesting consecutive chemistry. Meaning, silver 25 decreases in intensity, correspondingly Ag24Au goes up and decreases in intensity, 2 atoms substituted goes up in intensity, 3 and 4 and 5 and 6 happens, and finally an equilibrium comes up. So this is what you studied in physical chemistry, as A goes to B goes to C. So one can model all these kinetics. And these modeling kinetics will get you dynamics of the system. So today we model these. So just as organic chemistry reactions can be more organic, inorganic, whichever, you can model these. So while this kind of science happens, even more exciting thing happened in the lab. So here is a cluster. This cluster, I said, reacts with another cluster. Great. But you know, this particular cluster made of, let us say, silver 25, as it is moving, it is hitting on another silver 25, as it is moving. Is it not possible for one atom of this cluster to exchange with another atom of another cluster and become a new molecule? You may not see this because both are the same masses. Water and water. They exchange atoms. We know that hydrogen exchanges. But we can't see it. How do you see it? You see it by putting water, H2O and D2O. What you get is HDO. And I can study this dynamics. So can you not look at that dynamics? So we said isotopic exchange can be done. So here is silver 25 with 107 silver. Now you have to be a rich person sitting in labs like this because you can get 1 gram of this is 1 lakh of rupees. Not 1 gram of this, 1 gram of silver 107. 1 milligram, I'm sorry, 1 milligram of silver 107. So now you can get 1 milligram of 109 silver also. Right? You can get this. And you can make silver nitrate with it. Right? And you can then make silver cluster with it. We do that. So this is 107 silver 25 with some ligand, 18 of them. I get a peak and expand it. This is very similar to the mass spectrum of gold 25 I told you, because typical silver has two isotopes, 107 and 109. But if you have only 107, it is similar to gold because it has only one isotope. Mass spectrum looks similar of gold 25. The peak is 5142. Nanamani would love it. So he does mass spec. 5142. Now 109, 5192. The difference between this and this is 50 mass number. One silver is 2 mass number difference, 25 of them, 50 mass number difference, 5192. So these are two separate molecules, separate compounds. You make it, you can powder it, you can crystallize it, whatever. Now you mix it. This and this. So our prediction is that this and this, if you mix it, this should isotopically exchange and give you this. Okay? It should give you this. In fact, this is an experimental spectrum. And you wonder, how does this happen? You mix these two, you measure one mass spectrum, there is not enough intensity signal to get a good isotopic distribution, but this is what happens. Second spectrum, third spectrum, fourth spectrum. So you wonder, what is happening to matter at nanoscale? We never thought that gold and silver atoms can exchange so fast. I take your gold ring and then put a silver ring next to it. Nothing happens, right? Nothing happens. But at nanoscale, you bring it together, it's over. Atoms exchange super fast. Is it possible exchange dynamics can be studied? So we can study that, but in this particular case, the change happens so fast. So you have another ligand wherein the change is slower, another cluster where the change is lower. So this is silver 29. The exchange kinetics is slower, and we are looking at that concentration of a given peak as a function of time. Either decreases or increases or whatever, and you can fit it with rate constants, and we can get 3 rate constants. And the rate constants correspond to atom exchange at the surface, surface to bulk exchange, and the equilibration. So these rate constants are comparable to rate constants in organic chemistry. Rate constants in organic chemistry, people study this. Very exciting. Right? So now you ask this question, this is happening, fine, but does it mean that it is happening in bulk? So I have a nanoparticle which is thousands and 100,000 atoms and a cluster. Can atom exchange? Is it possible to have bulk powder and exchange? So we studied all of those. And it's so interesting that it happens even at any length scale. A small cluster and a bulk particle, it exchanges atoms. Because it pulls out an atom from here and you can see that peak coming up. So you can computationally model it. I'm not getting into these details. So lots of chemistry can be done that way. So you have a cluster, atom is exchanged, fine. One atom exchange, what you created is an alloy, right? So one more atom you can add, so you can get a 3 atom containing alloy. So you can get trimetallic alloys. So you can tetraatom. So you can do all that. So today we call this as high entropy alloys. So lots of new properties. So while this kind of science is happening, you can also ask this question, gold and silver is having something and they form an alloy. How about one silver and another silver, they react, 2 clusters and give you a 3rd cluster. So we do this kind of science. A lot more can be done. A and B react and give you a new cluster. You can do, reaction is a very broad term in chemistry, right? Interaction is a broad term in chemistry. So here is a cluster which is now protected with something called benzene, dithiol is a molecule. So it looks like this, benzene, 2 thiol groups, benzene dithiol. And this is with 29 atoms at the center. You can do supramolecular chemistry, create peaks. These are all C60 added. You can create assemblies. So I just showed you a cluster is assembled with C60. But one cluster can be assembled with another cluster. So here is something that we did. It is a gold nanorod assembled with something, clusters. And when you see a nanorod assembled with clusters, it gives you structures, and some of these structures become so uniform that you can do tomography. So you can model this. So on a nanorod, clusters assemble. How does it assemble? By hydrogen bonding. How is hydrogen bonding? Specific ligands. Is it 25 alone? Yeah, you can have large clusters. So lots of very interesting, exciting science become possible. I'm not going to go further. Should have time for some questions because so much should have already gone in. But clusters in general is having a shape. But there can be another cluster having a same shape. This is one cluster having 40 atoms, and this is another cluster having 46 atoms. Ultimately, they have the same shape. This is what it is from single crystal. How this happens? Because some of the inner atoms of 46 are not there here. That's what it is. Outer is all the same. So is it possible for you to put this and this and create a co-crystal? Yes, we can create that. What does this mean? This means that you can create a number of co-crystals. So your dictionary expands. More of materials come. So you ask this question, why at all I should study this in this laboratory? So one thing that happens in this lab is that we use materials for water. So this center itself is built on water. We create materials for affordable clean water. That's the subject of this place. So what we do are materials which are created as porous materials, and you pass water through this. So it is not just that we make some materials and leave it there. We take it to technology. So this is in the state of Punjab, which is in Amritsar district. So this water is going from this ground to this water tank, and the state government has found that it contains arsenic. Arsenic, okay, it can contain arsenic, but arsenic above limits. So arsenic above limits of what? Limits of something like about 10 times, 20 times the limit. So then what happens is that this was a mistake. So this arsenic that is present, they have been going around and looking for technologies. So we worked for many years creating technologies which are affordable. Today, this technology is now tested by World Bank. And they certified that this is the lowest cost technology. So World Bank gave money to Punjab. And so we installed purifiers across. In other parts in West Bengal and Chhattisgarh and Assam and UP and Bihar, and several places it has gone. Now this is there on Government of India webpage called Jal Jeevan Mission. So what is that? So you take this water, instead of passing it directly to people, you pass it through a set of filters in this blue box. So this is what we did. And that's in the background. But then if you have to do this well, you need sensors. So people have developed lots of sensors. So, if you have a Perkin-Elmer UV visible spectrometer, which can also work as a sensor. But this requires water samples to come to the lab. You have to have reagents to give a color change, etc. You know all the dye chemistry people do. But it's also important to develop sensors in the field. For example, this is a spectrometer developed by somebody in Korea. A visible spectrometer, not the electronics, light source, light detector, all of that combined together is just this much, 4 millimeters thin. 4 millimeters thin spectrometer. If this can be made 2 millimeters thin, it can go to a mobile phone. So what is so exciting about it? This spectrometer, you can shoot the spectrum of water and it comes online. In the lab we do, because this data are now compared with 1 million data. So now we have AI-based analytics to predict water quality. So lots of stuff is happening in this place, but how is it connected to clusters? So when water is passed through, clean water is passing and going homes and all that, we do sensors and analytics. Our clusters can also be used for that. This is a cluster which is put into a membrane and therefore it is luminescent. And this is now electrospinning based membrane. But you see, what you see is the change that happens to a cluster based fiber by exposure to mercury. So it is possible for us to create such sensors, but nobody, you wouldn't have heard about these sensors in the market. This is so sensitive that it detects 9 ions of mercury. But it cannot detect, or it is not put in the market. Why? Because clusters are metastable. They decompose. So is it possible to have stable clusters? Don't get me wrong when I say metastable. They are metastable in the sense that you can make a solution, you can make a crystal, you can do whatever, you can do some measurements, but well, they are not high temperature stable. They're not stable to 100 degrees. They're not stable in acids. They're not stable in bases. You can't put it into a polymer and compress it. You can't deform it. So all of these are important things in developing technology. So we were after this. So here is a cluster protected with a molecule called carborane. So it looks like this, beautiful. It's a crystal. But what is so exciting? This is high temperature stable. You see, 338.9 is the TG, thermogravimetry. It decomposes only at that kind of temperatures. In solution, it is stable up to 120 degrees. So we are now in an era where clusters are stable and therefore it can be used. So here is a cluster which can be stable and used. This is cobalt-6 cluster with ligands, 8 of them. So what is so exciting? You can make some deposited cluster films. So these are certain specific mesostructures that we created. Meso would mean that the structures are several hundred nanometers large. Individual clusters are tiny, but the solid state films that you make are composed of such particles. They have specific crystallographic planes. Using them, we can do electrochemistry and you can detect arsenic right from drinking water directly. So today, this is one kind of sensor we can have. But this is another one. This is copper. And this copper forms aggregates. And you will see more of these kinds of things from Amitava. These are luminescent. And this luminescence is affected by arsenic. Which means that we may be able to put this in the form of sensors in the field. By the way, don't get me again wrong. This is not in the market, but there's a company today working on this to develop pH-like strips. based on this. And they have gotten money to build that. So why is so exciting? So if you take the world is very big, as you know. These are all places with arsenic. These are all the concentrations. Some are high, some are very high, very less. Is it possible to create a map of the world with arsenic contamination? Somebody published a paper in Nature, in Science, with 200,000 data points of arsenic. With that, you could predict the arsenic concentration across the world. The same person published another paper with 400,000 data points of fluoride and predicted fluoride across the world. So what does that mean? Here is a place where there is fluoride, let us say some particular, this is whole country of Brazil. But there are many, many places here also similarly, the whole country of India, many, many places where we have data. We are building data. So your home has this particular problem, let us say, you write to the minister concerned, and that person could enable a technology to come to you. So that's the idea. The world could be like that. So lots of interesting molecules are made. So there is a person called Vivek in this group. He makes molecules like these. Beautiful molecules. I have no time. So I want to give some 20 minutes for questions. And very, very large clusters. There's another person who left the group. Very large clusters. This is 508 atoms are there in this. But today we have our computational capacity has increased. So this is now, you can calculate the orbitals of these entities. So we published very recently, it is written? No, it's all published. So, but then this is not the end. As material science is expanding, more and more mass spec and devices are coming. Very large clusters can be seen also with mass spec. So today, one of my students measured the mass spec of this. See, gold, what is this now? 2.4 million. Huh? No, this is 0.24, right? 0.246 million, 246,000 atoms of gold. So today, this way the subject is expanding. This is comparable to the mass of a virus. And viruses and mass clusters and all can be put to a technique called mass photometry. This is a device in the lab, you can see. This is scattering based mass measurement. 300 kilodalton to 5 megadalton is this mass spec device. You can see these clusters also, or large structures, also in TEM. So this is SCM of these large aggregates. So I have asked one of my students, in fact a postdoc, to measure the mass of this. And so she is in the process of doing that. There is another person in this group, her name is Harshita. She uses electrons diffraction to solve the crystal structure of clusters. So you have heard of X-ray diffraction to solve crystal structures. How about electron diffraction? So we do an electron diffraction is collected in a TEM. So she is sitting, where is she sitting? She is sitting somewhere there. Where are you? There, behind. So people can talk to you. So this is a TEM. It's called cryo-electron microscopy. There's one student here, who is probably not sitting in this room right now. This is an image of one cluster in different orientations. So using this, we can reconstruct the cluster image, cluster's real structure. This is called single particle reconstruction. So all of this is happening in that area. And how is the research now? There's a lot of things happening around, but you will be surprised. Lots of fellows across the world. Lots of fellows, lots of institutions. I have listed all of these people in India. There are many, many places, and here are our people. There's a lot of work that is happening in this place. So our people are, see, this is one person here. And Monday there will be somebody, it is written somewhere here, Monday. Yeah. But lots of places people are active on this. So this area is now expanding. You could expand this area. But where will you expand? So clusters can be made, etc. But actually we can do this with electronics. There are a lot of stuff that is happening in the lab on this direction. But if you start thinking about it, I'll quickly flash 2-3 slides just to tell you that we do not make enough of these. So if everyone wants to work on it, is there a place where I can go and buy some cluster? No, I don't. Make it. Make a company. Sell it. Lots of people can work on it. Do we know enough of it? Enough about it? No, we don't know. So lots of stuff can be done, and I don't want to mention more of these. So we do not make enough. So I started doing a pilot plant here, but we are not doing it now. But lots of things can be done. If you want to make applications of anything, you want to make grams, you want to make kilograms. So this is a person called Akira Fujishima. You might have heard about a person called something called photocatalysis. This is the father of photocatalysis, waiting for a Nobel Prize. So Fujishima once told me, if you want to do something, make in quantities. So this is his first slide, let us say. This is his paper, 1972. The next slide is this. That paper has changed the world. If you want to do something like that, you want to make materials. We just don't know deep enough. Deep into something we don't know. I can tell you more examples on this. We can discuss more about it. We do not know dynamics. We do not know mechanisms. In that, lots of exciting things are happening here in the group. Cluster is there, another cluster is there. Can you bring these clusters together in the gas phase? Cluster is an ion, another cluster is also an ion. This ion is called ionic adducts. So we have just submitted a paper on creating these ions, but this whole subject requires much more effort. To give you a tiny, tiny bit of that excitement, this is a person in Japan, in Tokyo University, Isobe. Isobe is making nanotubes. How? Reactions. Reactions by carbon-carbon reactions. You make this molecule. This is a molecule for him. By carbon-carbon reactions, he makes this and he solves the crystal structure of it. Are you not shocked? If you are not shocked, I am shocked by the kind of capacity to make molecules like these by chemistry. There's another friend of mine who makes this molecule. This, is made by nature, is made by some miracle process, but can you make it in the bottle by atom-atom reaction? So if you can do that kind of chemistry, any element here can be taken and make a cluster as you wish. That would be the dream of materials chemists. So lots of stuff can be done. If a molecule is known, like C60, some years ago I was sitting in a seminar hall, somebody comes and says that, this is C60, TM, of one molecule. How? Put that C60 into a nanotube and then look at it. And then he did a video of this. C60 is rotating inside. So imagine what all the things you can do with it. So much of unbelievable science can be done, And atomic precision, we will leave all these things aside. I told you sensors. This is India's map of water quality. Government of India is monitoring it. We are monitoring it too. But your village, is it there? No. Can we put all that on the map and create a water atlas of our country? Materials like these are important. Technologies are important. World is full of problems. Carbon fluorine bond is a great problem. PFAA. Can you break it? So here is, this bond is broken by one of the clusters that Vivek is making. I told you memory. Smaller clusters can be used for memory devices. So here is such a cluster, can make memory devices with it. Lots of, this is something that all not published, which means that lots of possibilities exist in this area. I told you atomically precise clusters are a new category of materials. They are molecules, lots of stuff to be done in nomenclature and all that. Clusters are thermodynamically stable, they exhibit unusual properties, useful properties as well. Atomic precision can be taken across periodic table. We are building an era of cluster-based materials. So molecular materials and functions can be done through such clusters, but several other molecules exist, several other functions exist. So you are seeing people here in this, many people from this group are here. But science of this kind cannot be done just by a few people. There are lots of collaborations that I have across the world and in different parts. But in other areas, I do have other collaborators. So my collaborators page is actually 3 pages like this. But just to tell you that you need to build your linkages. And lots of people have contributed and a great institution is behind. This was our previous director, this is the current director, lots of activities. So I'll leave this about 15 minutes or so. Yeah, thank you. You're welcome. You're welcome to ask whatever you like. Yeah.
Yes, so I was just wondering, that this it is taking to us. So I heard about this water purification as well. That is excellent. But I just want to ask if, as the materials are porous and all, so do you think of it as like CO2 captures and hydrogen gas storage and in that particular direction?
Yeah, so this area is expanding. There is a person called Sukhendu Mandal in Isar Thiruvananthapuram. There are also other people here. Now, I told you an example wherein cluster is the last example of memory devices. So this is a cluster. The message is that if you have a cluster which is with a ligand, now you connect it with a connector. Now this is assembled similar to a MOF, metal organic framework. In that you can put carbon dioxide, monoxide, nitrogen, what have you. Some of the metal atoms are exposed, so you can do catalysis. You can send in light because cluster will excite. Lots of stuff Amitabh does and all. So these excited electrons can be used for catalytic applications. So this area is expanding. So I can't tell you that somebody has made from a metal organic framework like structure using clusters, somebody has made CO2 to methanol. But people are on that. So now even more exciting would be that in a cluster, you can have, let us say, 5 atoms. So you can do, while making methanol, you can also make ethanol, right? By controlling, right? So you can also do tunability in catalysis.
One more small doubt. So, means how can you be so precise at the atomic level? Like, if I want to make a gold 24, per se, like you're
Yes,
talking
yes.
about gold 25, but if I want to make gold 24, then how can I be so precise at that level?
Yeah, so this is, if I go more deep into this, today it is trial and error. This is 23, by the way. Okay, but we have 24 also. But how can I predict ABC will get you 23 or 24, under what conditions? This is still a trial and error today. There are precise or well documented methods for making clusters today, but it has not become organic chemistry like to say SN2, E1 elimination. No, we can't today. That kind of precision, predictive power has not happened.
Can I go with one more?
You have time, but yeah, there's also, raise your hands. Yeah, go ahead.
So, in one slide you said that this silver cluster is weaker in ionization than the gold cluster.
Yeah, yeah.
So, on what basis that?
So let us say, for example, ammonium. Ammonium is intense. Phosphonium is not that intense. So it all depends upon to what extent this ion is stable in the gas phase. This stability or reduced stability depends upon several factors. Largely we say ionization cross-section. Okay. Just like optical absorption cross-section, there are ionization cross-sections also. It depends upon how, from a neutral state to the ionic state, how you can put something, and these are all thermal, quantum mechanical transitions. So you can compute it, ionization cross-section, but for this such large systems, you normally have experimental data.
Thank you so much. Thanks.
Atom, the question is, why is atom exchange happening? It is happening because, in the examples that I showed you, it is because of thermodynamic reason. The exchange system is far more stable than unexchanged system. So you are computing the free energy of this. So today it is that, but if you go further, the atom exchange is happening in, let us say, isotopes, isotopic exchange, where the enthalpy is not changing. What is changing is entropy. So entropy drives this. Exchange stuff has better entropy.
Can atom exchange happen between atom and metal and non-metal?
Those are things that you should do. We've just begun to do this. So for example, a silicon cluster and let us say an iron cluster. You exchange it. Do you have iron silicide? Yeah. So those are interesting experiments to be done. In the larger sense, exchange should be possible across whichever thing is thermodynamically and kinetically feasible should happen. Is something here? Okay, go ahead.
Sir, actually, my question is about the luminescence of your clusters. Like you have been talking about the displacement or replacement reactions when you mix two clusters. So I was expecting, or I have a question like, does the luminescent property change?
Every property changes. Okay, all properties change. I took mass spec because in this atom exchange, I am interested in whether atom is exchanged or not. Mass is the real proof. You can, of course, do crystal structures
Is
also.
it possible to make a tunable emission? Which
Absolutely,
could be used for
absolutely,
fluorescence
absolutely,
sensors?
absolutely. Yeah, you ask these questions to him later, but yes, tunability is indeed feasible. Right. Briefly introduce yourself. I am so and so from this place. Yeah.
So this is Somendarshi from CSI IMD Bhubaneswar. So sir, my question is that you talked about 900 atoms of nanocluster.
Yeah.
So sir, is there any kind of bottom line that above this it goes to like nanoparticles and below this it goes to like clusters?
Yeah.
Because for
Sure.
silver we have seen it's different from gold we have seen it different, from copper we have seen it different. So is there any kind of borderline from there?
There's lots of people have worked on in different techniques using these. So one way to ask this question is, at what size clusters become metallic? When it is becoming metallic, you become it as bulk. So metallic could be answered by people like Amitabha Patra would answer it in terms of whether it's, what about the electron dynamics? What is the time scale of this? Now somebody else will ask, how about conductivity? Will it show bulk like conductivity? Somebody else will ask, is there an occurrence of plasmon in this? Right? Somebody else will ask this question with whatever tools that they have. Originally, they asked this question, do you have a material whose mechanical property resembles bulk? Somebody asked this question, is this material whose thermal conductivity resembling like bulk? So depending on the technique you use, there are ways by which this has been answered or addressed. One yearly experiment that people did was melting point. This is somewhere around 1976. People started looking at melting point of nanoparticles. Now, later on today, when these atomically precise clusters are available, today we ask this question, is electron dynamics telling us something about its metallicity? Using such experiments, today we know around 140, 150 atoms, things become metallic. In the case of gold and silver. Now, there are also debates as to gold is lesser, silver is more, etc. Tunability is possible in these materials, gold, silver, and therefore a lot of data exists. You ask the corresponding question on platinum, I don't have. Corresponding question on iron, I don't have. Okay. Briefly about you and yeah.
Hello, sir. My name is Arun, and I am from Central University, Uttarakhand. Sir, my question is about wastewater treatment. As you said, if I will take something like biopolymers, right? If about nanocellulose, if I'm so, then how the crystal are in this direction? How crystal works with nanocellulose, the nanocrystals? How in this direction they works?
Yeah, so nanocellulose has been used extensively for wastewater treatment, water treatment and all that. Depending upon the type of cellulose, depending upon how nanocrystalline that is, depending upon how the arrangement of this, depending upon the functionalities of that you can graft on the polycellulose, lots of different materials have come. In the laboratory, we use nanocellulose assembled inorganic materials for removing fluoride, for removing arsenic. This thing has not become a technology today because there is inherently a problem that cellulose is a biomaterial and bacteria sit on it.
One question more. Sir, as you said that nanocellulose, right? My question is that, sir, question. I just forgot.
Question will come back. We can go back to that later. Yeah. Yes, behind. It's okay. We are just about 2 minutes left. Yeah.
Sir, my name is Devan. I'm from IIT Kharagpur. If you remember from your last visit to IIT Kharagpur, I met you there. My question is regarding that regarding the control of the clusters that we are getting. You showed us the variation of mass spectroscopy, how each atom is being changed by slowly adding a little bit of gold. Sir, my question is, if we want to get exactly that cluster in which two atoms have been exchanged, what stage of control do we stand on today, and what is the theoretical possibility of extracting one single cluster from such a varying process? That is my question.
So you are asking the question, gold 25, you can make AU24, AG1, AG2, AG3, 4, etc. Can I make just the AU22, AG3? this precise stuff that you wish to have from a reaction mixture. This is now Pandora's box today. It has not been solved. For example, such a cluster that you, even if you make, tomorrow you come back, it will exchange atoms again. It will become 2 and 1 and all that thing. So this is what people have studied today. So it's difficult to create such a cluster and keep it in a bottle and assume that nothing happens. That has not happened. So you need to, probably we need to discover new ligands wherein some change happened and then you freeze it in that condition. Okay? That we should close it here now, and just to tell you that I am around and others are also around, so you can always ask questions.